I would like to thank, first of all, Dr. Bardea and Dr. Zach and Professor Zach for inviting me here. It is indeed an honor to be here and talk a little bit about what we do in Albit with nanotechnology, and especially regarding applications, energy applications. So, as I'm the one who is actually keeping you from the coffee break, then I will skip and skip very fast the introductory slides regarding nanotechnology and its very important role in increasing the energy efficiency of devices. Nanotechnology, and especially nanotechnological processes and methods for implementing novel materials within a variety of devices, actually somehow come with us together from the energy sources, going towards energy conversion, energy distribution, energy storage, and energy use. What I will talk about is more the red box here regarding the energy storage, and especially electrochemical energy storage. Of course, I will not focus on all the variety of devices, starting from electrolytic capacitors and ending with fuel cells. What's going on? I will focus more in a certain technology that we are actually developing within Albit, which is called supercapacitor. Albit entered in terms of a strategic point of view the energy field approximately 6 years ago, when they decided to enter the energy field. The reason was the lack of power solutions for usually military applications, but afterwards they found out that also the civilian market lacked those kind of power applications. So the technology that they decided to focus at that time was the supercapacitor technology. And why supercapacitor technology? Because supercapacitors are they have high specific power density, and they know, but on the other hand, they have relatively low energy density, but their strength is based on the fact that they know how to release this kind of energy with a very short period of time. And when we are talking short period of time, we are talking about hundreds of microseconds. When you take that and compare it to a conventional battery that it takes several minutes up to hours, then you can see the orders of magnitude. As I said, it is important for me, and I feel privileged to be here, first of all, and secondly, I would like to acknowledge that all the nanovision within Albit system was the initiative of Mr. Chaim Russo, who was the former CEO of ELOP, Albit's electro-optic division. And after that, he became VP technology in terms of Albit systems, in terms of the corporate. And as a great man, he had a very pioneer vision implementing nanotechnology methods and techniques in Albit's core business products. And actually, he was the one who pushed forward and pushed very much towards the implementation of nanotechnologies also within energy devices. And as I said, there is a strong motivation for those nano-enabled energy systems. And when you talk about the implementation of nanotechnologies, first of all, you talk about ultra-small energy systems, because of the ability of nanotechnology to shrink the size and the weight of those systems. So, and by that to increase the specific energy and power density, also in terms of the gravimetric, in terms of weight, and also in terms of volumetric, in terms of volume. But what I would focus here today is more macro scale energy systems, specifically talking about larger systems that their properties are enhanced with nanoscale structures. And as I said, I will focus on the supercapacitor technology, which was the core technology that Albit Systems decided to focus on 6 years ago when they opened this business unit termed Energy and Power Department. Today, the mission profile of the unit, which also has been increased and enlarged, also has been increased. And what we look more into providing hybrid products for turnkey solutions in terms of system solutions. Albit is a house of systems, so that's what Albit knows how to do: provide systems. And energy and power packages are only a part of that system. Specifically, the business unit started with a supercapacitor technology, and lately, in the last year, we have purchased the properties of alkaline fuel cell technology, and both technologies are implemented within our business unit. And I am very happy to be involved with the R&D and in charge of the R&D of both activities. When I'm just going into some fundamental differences between power versus energy, and the difference between power and energy is the difference that actually specifies the variety of electrochemical energy storage devices. And in terms of the how to map them, or how they are located in this, in terms of their power and energy density, a very good way to place them are following the Ragone plots. And these plots actually plot the energy density in the y-axis and the power density in x-axis, or vice versa, depends in which book, from which book do you take them. But what is important to see in those plots is that you have the conventional capacitors in this part of the plot with very high power density but relatively very low energy density. You have the batteries, and here somewhere further the fuel cells with very high specific energy density and relative low power density. And somewhere supercapacitors bridge between those two sources. What is the the uniqueness, let's put it like this, of Albit supercapacitor, and how does it differ from other conventional commercial capacitors? What we have, the technology that we have developed is actually based on an aqueous electrolyte and not an organic solution, as usually is done in other commercial supercapacitors. The implementation of an alkaline aqueous electrolytes gives us a certain set of benefits in terms, first of all, of the cost effectiveness. We are talking about a very cost-effective solution in comparison to organic winded supercapacitors. The fact that we use an aqueous electrolyte, meaning the size of the ion is very low, gives us the possibility to reach the best potential of the electrode material, which is usually made of activated carbon with a very large surface area, and those small ions can actually penetrate and access each and every pore of this activated carbon, which means we can get maximal capacitance. The conductivity of the alkaline electrolyte is much more higher than let's say organic solutions, which means that also in terms of the inner resistance actually is very low. That means that the response time is extremely rapid. In terms of the configuration, it is a stacked bipolar configuration, which means that each cell actually is stacked and in a certain package, and that means that it is very flexible in terms of tailoring the properties, both in terms of power requirements as well as energy requirements. And you can treat it as usually a Lego building block that you can put them in series or in parallel, very versatilely, a very versatile solution. And in that case, you can actually fit your capacitor to the demands of the customer or to the demands of the system. And this is very important when we talk about implementing solutions for a system.
How do you get to -46 with aqueous solution?
With aqueous, actually, we are using a certain concentration of the alkaline solution, which is fitted to the phase diagrams, and the freezing point of that specific concentration is beyond -50. So, but it has to be at the specific molarity and at the specific. Once you divide by only, let's say, 5% into both directions, then you will not achieve that stability. But actually, this is one of the strong point of this solution in comparison to the commercial organic supercapacitors, which actually suffer at temperatures beyond -20, -30, and in order to come over that limit, then they usually implement more, let's say, in terms of the design, a thermal insulation, so that actually they will not be so sensitive to the temperature. And this is one of the strong points of this kind of supercapacitor, because due to this aqueous electrolyte and also due to the bipolar stack configuration, which makes it with a very lower ESR, which also is less sensitive to temperatures. And one of the applications that, when you look at the overall market segment, and of course you have the static energy storage, which was the commercial, the conservative previously used application for supercapacitors, but with actually with the emerging of the electrification of transportation, then you see more and more potential and possibilities for implementation of supercapacitors in the transportation segment. And one of the strong points of having a supercapacitor in a transportation segment is the fact that you can do cold cranking. And coming back to what Professor Resheftene actually said, one of the strong point of the supercapacitor is to know how to give this burst of power and to take the peak power from the battery in the car, and be able to do it also at very cold temperatures. And we have projects, especially in the northern part of America, with clients there regarding the application of putting together a supercapacitor with a battery, just in order to provide the cold cranking of the car or of the truck or the certain vehicles. So you can so the major market where supercapacitors are focusing today is the transportation market, and you can implement them starting from hybrid vehicles with the start-stop regulation that has become a regulation in Europe. You know, you just stand in the traffic lines and then your car stops. It's very annoying, but it is a regulation. So there, the combination of a supercap with a lead-acid battery, for example, is very beneficial, because the supercapacitor does not only take the peak power and by that increasing the battery lifetime by a factor of 2 or 3, depends on which kind of supercapacitor you use and which kind of and the profile, of course, the the driving profile, but also it's very important for regenerative braking. So in those, so you can start implementing supercapacitors starting from your private vehicle and going back to heavy-duty vehicles, trucks and trains and trams. And there is a project regarding the implementation of supercapacitors within electric urban transportation. And there is a project that Elbit is a demonstration project that Elbit is leading in demonstrating the implementation of a bus, electric bus, who is going to it's a shuttle bus, for example, that will go to a certain route. The energy is given by supercapacitors only due to the ability of the supercapacitors to release and to be charged and discharged at a very short period of time. So the idea is, and since in the profile of a bus you go from one station to another, and the distance between stations is relatively very short, 1 kilometer, 1.5 kilometers max. So we are not talking about driving for large distances. For that you need a lithium-ion battery for sure, but for these short distances from one bus stop to another, when you have the ability of a supercapacitor to be charged very fast during the time that the passengers are coming into the bus. So this could be, this is a project that we are going to demonstrate, hopefully in the shuttle between Beit Yehoshua train station to Netanya, Elbit's Land and C4I quarters, but there are some rumors that maybe it will be from at the airport when you put the car at long distance and to the. But nevertheless, it's a very nice idea because you have, and it's a very nice project in terms of the development, because you don't need only to develop the supercapacitor, you also need to develop a fast charging method, a fast charging infrastructure, which is very interesting in terms of the engineering, and there are a lot of ways how to fast charge, and one way it's via induction, and there are a lot of nice ideas that you see being implemented somewhere in different parts of the world, and we are very enthusiastic into dealing with this project, also in terms of the curiosity and the implementation of novel ideas. So going back to the energy goals, or power and energy goals, these are the Ragone plots, and where is the market pain? Everyone wants to be here in this red ellipse over here with the largest energy density and the largest power density. And how can you do that? Well, you can do that in a very simplified way by hybridization of systems. So this hybridization can be either mechanical, external, or electronic. So you take a battery and you couple it together with a power source, such as a supercapacitor, and usually you have to take care about the battery management system, and so you have to control which device takes the certain power or energy demands of the system, and how to control it, so you can do an electronic hybridization. But what is more interesting in terms of materials is how to do an intrinsic hybridization. How can you deal with the materials inside your device so that on one material you have a battery type-like behavior, and on the other material you have a supercapacitor type-like behavior. So you can have a hybrid system within your own device. And this is what I would like to talk about. Starting with what I previously said about mechanical or electronic external hybridization, we have a solution that we call BATCAP. And as you see, there is this lead-acid battery with a supercapacitor. It can be either in terms of unified in one model, or it can be an external connection, and this is actually the most it is the most demanded one, because then the supercapacitor, usually the one being put here, has the ability to live for 10 to 15 years, but the battery usually lives for 2 years, and with the supercapacitor inside, then its lifetime is multiplied or even tripled. But nevertheless, you can exchange the battery and leave the supercapacitor. This is why we thought about this kind of solution instead of this kind of solution. But this is a very cost-effective approach that is being field tested in different customers, especially due to these regulations of start-stop application. It's very cost-effective, also in comparison to other solutions that are in the market today, and it provides the battery a very long cycle life. We are talking about 65,000 cycles at a 3% DOD of the battery, and 240,000 starter cycles. These are the USABC, it's the consortium of GM and Ford and Daimler Chrysler demands. And these are the demands for start-stop application today. With some, each one has a slight derivation, but actually these are the common demands. And of course, you have to have a very wide operational temperature range from -46 up to 65, and be small in size. So this is actually how we address this kind of external or mechanical and electronical hybridization. And now I will talk a little bit about the research that we do in terms of the internal hybridization or intrinsic hybridization within the electrodes. We conduct a variety, and we do not do this research by ourselves. We of course have the facilities, the manpower, and the investment of Elbit, but we don't do it by ourselves. We do it with we have extensive, fruitful collaborations with every university and electrochemical group within those universities in Israel, and a lot of collaboration with research centers and universities abroad. Part of those activities are funded by the Israeli Chief Scientist Office, and part of those are funded by bilateral foundations. And the focus of our research lays on the design of novel capacitive storage materials, starting from modified activated carbons that they serve as electrode materials, moving forward to implementing nano oxides and designing a pseudo asymmetric supercapacitor, application of carbon nanotubes in order to achieve improved performance. We were involved for in a 5-year consortium headed by Rafi Koriat, where also Rafael and Tasia Virit, Plasan were involved in implementing CNTs for a variety of applications, and we were leading the energy cluster. In these days, we look at graphene. We have some research activities on graphene as potential electrode material, and implementing ionic liquids as novel electrolytes that will enable us to achieve a high cell voltage and by that increase the energy density. As I said, we conduct state-of-the-art research under the Israeli chief scientist with different groups in universities, Professor Peled and Golodinsky. We had the pleasure working with Gil Rosenman and Ehud Gazit from Tel Aviv University. From Bar Ilan, we work closely with Doron Orbach and Lalouche. From Hebrew University, strong collaboration with Shlomo Magadassi, and in Technion we worked with Yachin and Narkis and Yuval Yaish, and today we work with also with Yoed Sur and Yair and Eli. Some examples of what we have done by implementing, for example, CNTs and designing composite activated carbon and CNTs electrodes in order to get better rate capability and charge utilization. We started in the beginning when the CNTs emerged. The idea was, oh, you have these great materials in terms of the electronic conductivity, in terms of the strength, and the idea was to implement them as electrode materials. We found out that especially for the design of our own electrodes, when you take CNTs with a specific area of, let's say, 400, 500, up to maybe 600 square meter per gram, and compare it with low-cost activated carbon with a specific surface area of above 1,000 square meter per gram, then, of course, in terms of the surface area, they cannot compete. The surface area of the activated carbon is good enough, and if you have a optimized ion size of your electrolyte that gets to each and one of those pores, then you will achieve the optimal capacity. But where is the great strengthness of those CNTs and their implementation? As I said, to achieve this better charge utilization, and we started in the beginning we started to grow them, but then we said, okay, maybe we'll just put them within our electrode materials and try to disperse them via sonication. And we started with very large concentrations, 25%, etc. And we found out that they had a tendency to aggregate. And then we said, okay, we will lower the concentration, because in that way we will ensure a better homogenized dispersion, and it can be done either via dispersion or via mechanical ball milling and mixing. And we saw that the inner resistance, due to only 5% CNTs implementation, was decreased by 28%. The capacity increased at low current operation by only 10%, but the good point is that at high current operation, and when you look at those transportation applications, that's what you need, high power and high current operations, the capacity increased by 50%. An increase of a capacity by 50% means that the energy density is increased by 50%. So regarding the intrinsic hybridization, or the design of an asymmetric pseudocapacitor, I would like to talk about a nice product that we have developed, and it's based on manganese dioxide material. It's a pseudocapacitor. Why it is called pseudocapacitor? Because usually in a supercapacitor you have the charging storage mechanism is based on electrostatic charge. Nothing changes. Nothing is nothing is irreversible in terms of the electrode material. This is why the supercapacitor have the capability of providing 1 million cycles and a long lifetime in comparison to batteries, where they have these redox reactions that actually somehow degrade the behavior of the electrodes, and that's why their lifetime actually it's lower by orders of magnitude. So what we did, we implemented this asymmetric configuration, and we instead of having 2 carbon electrodes, then we had this manganese dioxide electrodes coupled with a carbon electrode, and this is what we achieved in terms of the capacitance. This is the cyclic voltammetry, this is the standard symmetric configuration, and this is the asymmetric configuration. You receive, for example, we did some acceleration tests in order to see what happens. We found out that when you have a supercapacitor without CNTs, there was an acceleration of the reactions, which was, you can see that after 5,000 cycles, it died. So the specific capacitance drops very drastically, and also the inner resistance increased very much. And then we said, okay, we will put into the cathode some CNTs. And then we saw that the initial ESR was decreased, and after that, what was more pronounced was the prolonged cycling at accelerated temperatures. We did some post-mortem analysis, and we saw that the degrading phenomena, the failure phenomena that actually is the dissolution and and this flake phenomena that comes due to the dissolution and precipitation of the manganese dioxide grains due to the cycling was somehow reduced, because you have this CNTs serving as a strengthening net, this is our assumption, that keep the cathode together. So these are some ideas about implementing graphene, and this is actually IMOD funded project with Albit, and we have a partner in Singapore that we work with. Here the idea is to get at specific energy densities beyond 20 watt-hour per kilogram and power densities of 10 kilowatt per kilogram. And another area that we are focusing is in going into the organic world, but not organic per se, but using ionic liquids, which are the advanced green organic solvents that have the ability to have a very high electrochemical stability, up to 4.5 volt. And the idea is there are a lot of challenges in terms of the implementation of these ionic liquids, especially because these are very viscous, they have a very good behavior at high temperatures, but they have a very bad behavior at low temperatures beyond -20 centigrades. And of course the conductivity is a very big issue. But there are ways to tackle it, and we believe that at the end of 2017 we will achieve, at least in terms of engineering prototype, the desired energy density of 20 watt-hour per kilogram, the number of cycles that have to be beyond the 20,000 cycles, without actually reducing the specific power density that we have today within the aqueous capacitor, which is somewhere at around 1 to 3 kilowatt per kilogram. So and I would like to finish with this, that one can get there only by implementation of advanced materials research and nanotechnology, and we believe that we can get there. Of course, not being in this upper part, but maybe being in this lower part within the next future. So thank you very much, and it was a pleasure being here.